In this lesson, we're going to go through some of the basics of probability. So probability is defined as the chance an event will occur in a very long series of repetitions. And this is for if all the outcomes in a sample space are equally likely. The probability of event A is equal to the number of outcomes in event A over the total number of outcomes in your sample space. The probability of an event occurring, okay, so we use capital P, probability of an event, it's written like this, is always between 0 and 1, where 0, to put a 0 here, means that it's impossible, and 1 is that it is certain to happen. Few things are 0 or 1. Usually it falls somewhere in between. I want to introduce the vocab word complement. So, event A. Let's say this is event A, and this is that little set right there represents A. Everything outside of it would be the complement of A. So let's say the event A is the chance that it's going to rain. So the probability that it's going to rain versus the probability it's not going to rain would be the complement, A complement. So A complement is defined as 1 minus A. Okay, some vocabulary over here. Trial, outcome, and event. So when rolling a die, one roll would be a trial. Your outcome is what you get. So you would get a 1, a 2, 3, 4, 5, or 6. So the outcome is your result, where your event is like what you're looking for. So it could be the probability of rolling an even number. So that would be written as probability of rolling even, or you might even just say probability of even. Okay, some non-examples of probability. Your textbook talks about the law of averages, meaning there is no such thing. We have the law of large numbers, which says probability is a prediction over long-term results when we do something many, many times. Probability says nothing about short-term. Often you hear people say things like, something is due to happen because it hasn't happened in a long time. But probability is only about many, many, many times. It's nothing about short term. There are two major types of probability. We have theoretical and empirical. So theoretical is probability that comes from a model, and it's based on a sample space, which is a listing of all possible outcomes. Often we make tree diagrams to see that. Empirical probability is sometimes more informally referred to as experimental probability. It's when we actually simulate an experiment. So the law of large numbers states that the simulated or empirical probability tends to get closer to the true probability as the number of trials increases. So if we don't know the probability of something occurring, what we can do is we can actually simulate the event. And if we do it many, many, many times, then we know that over time it's going to get closer to theoretically what's actually occurring. So here's an example about commercial airplanes. So commercial airplanes have an excellent safety record. Nevertheless, there are crashes occasionally with the loss of many lives. In the weeks following a crash, airlines often report a drop in the number of passengers, probably because people are afraid to risk flying. Part A. A travel agent suggests that since the law of averages make it highly unlikely to have two plane crashes within a few weeks of each other, flying soon after a crash is the safest time. What do you think? So the law of averages is nonsense. There is no such thing. Probability does not predict short-term outcomes. Therefore, it cannot be said that it is safer to fly shortly after a crash. In Part B, if the airline industry proudly announces that it has set a new record for the longest period of safe flights, would you be reluctant to fly? Are the airlines due to have a crash? Well, I think we can answer this very similarly, that probability, again, does not predict short-term outcomes. We can't say that the airlines are due to have a crash. But despite this, I think that people have this misuse or misunderstanding of how probability works, and they do come up with this false sense that something is due to happen. Example 2 says, many stores run secret sales. Shoppers receive cards that determine how large a discount they get, but the percentage is revealed by scratching off that black stuff. What is that stuff? Only after the purchase has been totaled at the cash register. The store is required to reveal in the fine print the distribution of discounts available. Which of the probability assignments are legitimate? So let's look at A. Well, first thing that jumps out at me is that these do not sum to 100%. So since it does not total 1, I'd say A is not legitimate. I would also say B, well, it looks like that's greater than 1, so that doesn't work. C, the probabilities, C looks legitimate. That one looks okay. They have a total of 1. D is nonsensical because you can't have a negative probability, and it also doesn't add, well, actually it would add to 1, so, but no negatives, no negative chance of something occurring. It has to be between 0 and 1. And it looks like E is legitimate. It's not a very kind sale. I think that they're deceiving their shoppers, since everybody's getting the chance of 10% off, and, you know, bogus sale, somebody might catch on, but it is legitimate. Example 3 states, in a large introductory statistics lecture hall, the professor reports that 55% of the students enrolled have never taken a calculus course. 32% of the students have taken only 1 semester of calculus, and the rest have taken 2 or more semesters of calculus. The professor randomly assigns students to groups of 3 to work on a project for the course. What is the probability that the first group mate you meet has studied, first of all, 2 or more semesters of calculus? So if we look at our given information, that they've never studied is equal to 55%, that they've had 1 semester is 32%, and 2 or more is equal to 0.13. So there's a couple ways that you can think through each of these, but 2 or more semesters, well, that's really given to us. That's just 0.13. Some calculus would mean 1 or more. So we can, just proper notation, I'm just going to say 1 plus is equal to 0.32 plus 0.13, or 0.45. And then no more than 1 semester of calculus would be the probability of having 0 or 1 semester, which would be 0.55 plus 0.32, which is 0.87. You know, you could think this through as far as the complement as well. You could say, well, it would be 1 minus 2 or more. 1 minus 0.13 would also be 0.87. So there's quite a few ways to think these through. So let's give you another definition, mutually exclusive events. So mutually exclusive events are 2 events that cannot possibly occur at the same time. And the notation you see on your screen is the probability of A union the probability of B. If they are truly mutually exclusive events, you can just add the 2 probabilities together. A Venn diagram would be there's absolutely no overlap between your 2 events. So it's important to note that if I asked you what was the probability of A intersected with B, this is equal to 0 because there is no overlap. Decks of cards are easy to understand mutually exclusive events. So if I asked you what's the probability of drawing a red or a black card, well, a card can't be both red and black, so the probability of it being both would be 0. Now, something that's not mutually exclusive would be, what if I said, what's the probability of getting a red or a queen of hearts? Okay, so this is not mutually exclusive because there is overlap. A queen of hearts is a red card. Now let's talk independent events, and we're going to revisit this. We're only going to talk about this in the most simplest way right now. And this is where the probability of event occurring does not change the probability that event B will occur. In other words, one has no impact at all on the other event. Notice your notation, the probability of A intersected with B, and it says that we just multiply these together. Now, many statistics methods require an independence assumption. Okay, so you have to at least think about, and you should state that, okay, these are independent events and state why. So it's reasonable to use the multiplication rule. So a Venn diagram could be that we have two events. It is possible there is overlap. Okay, so this is the probability of A intersected with B. Simple scenario of two independent events would be, what's the probability of drawing a red card and a black 10 from a deck of cards? So my first draw has no impact on my second draw. So it's kind of like I'm doing two events here. So we reach in, probability of a red would be half the deck times probability of a black 10. Well, there's only one out of 52 cards in a deck. Now, that quick example would be assuming that I replaced the first card. If I didn't replace the first card, that second probability would be 1 out of 51. Okay, so we are going to go through a few textbook questions here. And in chapter 14, it talks about a stoplight example. It says, we opened the chapter by looking at the traffic light at the corner of College and Main, observing that when we arrive at the intersection, the light is green about 35% of the time. So the question is, if the probability of green is equal to 0.35, what's the probability that the light isn't green? Well, probability of not green, I'm just kind of emphasizing some notation here, of not green would be the same as the probability of green complement, also sometimes said not green, and that's equal to 1 minus the probability of having green, which would be 1 minus 0.35 or 0.65. So I know that some of you are going to want to jump right to just an answer, but get in the habit of showing notation. So when you get to the light at College and Main, it's either red, yellow, or green. We know that the probability of green is 0.35. Suppose that we find out that the probability of yellow is about 0.04. What's the probability that the light is red? So probability that it's red would be equal to 1 minus the probability of green union yellow. Okay, and that's the same way as saying or, probability of green or yellow. These would be mutually exclusive. So green or yellow would just be add the two together, 0.35 plus 0.04, and then you're going to take that away from 1. So this is going to be 0.61. We've determined that the probability that we encounter a green light at the corner of Main is 0.35, yellow is 0.04, and red is 0.61. Let's think about your morning commute in the week ahead. What's the probability that you find the light red both on Monday and Tuesday? First of all, I would say it is okay to assume independence here, because what happens on Monday is not going to impact how the light changes on Tuesday. So I'm going to say the probability that it's red on Monday and red on Tuesday, that I can assume that since these are independent, this is the same as finding your events separately and multiplying them together, which would be equal to 0.61 times 0.61 or 0.3721. Next we said, what's the probability that you don't encounter a red light until Wednesday? So let's think about what that means on each day. That means that on Monday, it would be not red. Or I could say red complement. So this would be Monday. And again, we're assuming independence times the probability that it is not red, or red complement, on Tuesday. And then Wednesday, it is red on Wednesday. So using the idea of a complement, it would be 0.39 for Monday. For Tuesday, the same thing. And then Wednesday, the probability that it is red would be 0.61. So let's see if I put this in my calculator, taking it out a bunch of decimal places. That's pretty unusual. 9%, approximately. All right, what's the probability that you will have to stop at least once during the week? Now I want to give you a clue. Whenever you see this phrase, at least once, it is usually easier to use your complement rule, because at least once means that you could stop it once, 2 times, 3 times, 4, or 5 days in a row. So it's easier to figure out the chance of 0 stops and then subtract that from 1. So we're looking at what's the probability of at least 1 stop in 5 days. Well, this would be equal to 1 minus the probability of no red lights in 5 days. So if you think about this, this would be probability of no red intersected with no red. Maybe I'll make this notation more obvious. No red again, and no red all the way up to 5 days. That notation helps me see a little bit easier that, oh, what am I actually doing here? I'm doing 1 minus, and the probability of no red we saw was 0.39, so I multiply that for each day. So no red on Monday, Tuesday, Wednesday, all the way up through Friday, so 5 days. And usually somebody says, can I just do 1 minus 0.39 to the 5th? Absolutely you can. They are equivalent. So, and of course I'm saying 5 because we've got 5 working days, and this would be equal to, toss this in the calculator, approximately 0.991.